Hey guys, this is a mini lecture about water potential. In this lesson, remember, we are talking about cells that have a cell wall, so plant cells. And in plant cells, the cell wall prevents the cell from bursting. And remember that this is different from when we talked about the red blood cells, because if too much water came into the red blood cell would burst. Because a plant cell has a cell wall, instead of the cell bursting when water comes in, it actually puts pressure on the cell wall. And so when we're talking about osmosis in plants, we have to take this pressure into account. So anyways, pressure will build up inside of the cell. When the pressure inside of the cell becomes too large, becomes large enough, then no additional H2O will accumulate. It will be in dynamic equilibrium with its surroundings. And that is when the plant cells are happy. That's when they will be turgid and they will be stiff so that the plant can stand up. Movement of water through plant tissue cannot be predicted simply by knowing the solute concentration. And this is different than when we were talking about these red blood cells. When we were talking about the red blood cells, if there was a high concentration of solute here, low concentration out here, we automatically know that water is going to move towards the high concentration. In plants, it's not that simple. Because of that cell wall. So we use water potential to figure out which way water will flow into and out of plant cells. And it's used to predict the direction in which water will diffuse through living plant tissues. Water potential, it's the tendency of water to diffuse from one area to another with regard to, it takes into account solute concentration just like we're used to, but it also has to take into account physical pressure because of that pressure that the cell wall exerts. So free water moves from regions of higher water potential to regions of lower water potential. And that's really important for you to remember. High water potential to low water potential. And when we're talking about the water potential equation, this symbol right here, psi, that's how you say it, psi, like psi, that means water potential. And the units we use for psi is either megapascals or you will see bars. We're talking about pure water when there's no solute. The water potential of pure water equals 0 megapascals or bars. So if we look at this example over here and we have low water potential on the inside of the cell, high water potential in the solution it's sitting in, we know that free water moves from high to low, so water will move into the cell. Seems easy, but there's more. We need to take into account the solute concentration and the pressure potential. So this is the full equation for water potential. And this psi with the little s right here is solute potential. You will also see it written as osmotic or osmotic potential. And again, it's called osmotic potential because we know that we know how water moves in regards to solute, and that's osmosis. So osmotic potential. And this other symbol here, the psi p, this is pressure potential. And this is taking into account the pressure that is exerted. Solutes in plants, what usually is dissolved in the water is either ions, we'll see ions. For example, if sodium chloride is dissolved into the water, then it dissociates into sodium and chlorine, and these are ions. and sugar. We see this as sucrose most of the time. When these solutes are added, they bind water molecules. As a result, there are fewer free water molecules. And let's make sure we understand that. So if we put sugar into water, we know that water wants to, if it dissolves, the water surrounds it. And so if the water is surrounding it, then that is decreasing the amount of free water. If we put salt into the water, so if I put NaCl into the water, I'm not going to make Cl blue. I'm going to make it yellow. It dissociates in water. So you should have learned about that in chemistry. So it's actually going to dissociate into ions. And then water, again, because of its polarity, is going to surround those ions, again, decreasing the free water. And so what this does is it reduces the capacity of water to be able to move, because some of that water is being tied up because it's not free water anymore. And because of this, there's a decrease in solute concentration. Sorry, I did that backwards. I'm sorry. An increase in solute concentration is going to make this more negative. So it's going to decrease the water potential. And again, that's because of the free water. So if we look back up here, when we look at solute potential, it's always going to be a negative. And that is because it's reducing the amount of free water. So as water solute increases, this becomes more negative. I forgot to fill this in. Directly proportional to it's up here. This is its molarity. And so just to refresh your what molarity is just a concentration. All right, so let's keep going. So again, here's our solute potential, here's our equation. So when the including summer, this is going to be turgor turgor pressure. Oh, sorry, I forgot what I was supposed to put there. Now I remember. When the living parts of a plant cell, so that's talking about the inside, the plasma membrane, the inside of the cell, when that is pressed up against the cell wall, that creates turgor pressure. So remember here, water moves from what water potential? From high water potential to low water potential. So let's take a look at this little example right here. If we have high solute out here, we know that water is going to move out. But in pure water, we know that there's going to be a higher solute concentration on the inside of that cell, so water will move in. As water moves in, it's pushing against that cell wall, and that pressure against the cell wall is called the turgor pressure. So let's look at this example. In plants, if we have a flaccid cell, so remember that's when it's like kind of limp. So if this is a flaccid cell right here, and it is put into a 0.4 molarity sucrose, we can calculate. So it's giving us here the pressure is 0, the solute potential is negative 0.7. Here, on the outside, there's still no pressure, and solute is negative 0.9. So what's going to happen? We go from a high water potential to a low water potential, so the water will move out. If we put that same cell inside of pure water, what's going to happen is the water is going to move in, because again, pure water has no solute, so the water is going to move in. And it's going to create this pressure inside of the cell. When that pressure equals the solute concentration, so here you see 0.7 and negative 0.7, then we are at equilibrium. So that's when the water will be moving in and out at the same rate. Water potential is 0 at that point. So let's keep going. There's more to this though, because you're going to have to calculate this. So there's more to the equation. If we need to figure out the solute concentration, this is the equation you use. So solute concentration equals negative, don't forget that negative ionization constant and this is talking about the solutes and if they ionize. So for sucrose, it's always 1 because sucrose does not ionize in water, but for NaCl, it ionizes into Na and Cl. So that ionization, you will use 2 for that. C in this equation equals the molar concentration. R is a pressure constant. This is given to you on the equation C. It's 0.0831 liters bars over moles Kelvin. And then temperature for this equation, you have to use Kelvin. So remember, it's Kelvin is 273 plus degrees Celsius. So let's do an example of this. If you have a 0.2 molar concentration of sugar solution in an open beaker, calculate water potential at 72 degrees Celsius. So if we want to do this, we know that water potential equals the solute potential plus the pressure potential. It gave us a concentration and it gave us temperature, but it didn't give us the solute concentration, solute potential. So we need to figure that out in order to do our equation. So here we know that Ys equals negative I. Here we know that we're talking about sugar. So sugar, it told us up here, is negative 1.0. And then we are going to multiply that by C. And it gave us C, 0.2. And it gave us molar. And we know that molar is actually moles over liters. And then we have to plug it in for our R, which it gives us. It is 0.0831 liters times bars over moles times Kelvin. And then we have to add in our temperature. And our temperature is, it gave us degrees Celsius, so we have to turn that into Kelvin. So it is 273 plus 72. And that is going to be in Kelvin. So if you multiply this out, let's first just look at our units. So moles are going to cross out, liters are going to cross out, Kelvin is going to cross out. We're left with bars, which is good. And then you just multiply this across. So remember, don't forget this negative. We'll do that at the end. So it's 1 times 0.2 times 0.0831 times 273 plus 72. This is actually going to equal 345 Kelvin. Multiply all that out and multiply by the negative. You're going to get negative 5.7339 bars. And that is going to equal our solute potential. Well, it told us that we are in an open beaker. So when we're in an open beaker, there's no pressure. So we can get rid of that. So now we know that water potential equals the solute potential. So now we know that our water potential of this is going to be negative 5.7339 bars. Okay, so let's keep going. So let's use that same cell that we just calculated the water potential for. In its place in a beaker of sugar water. So beaker of sugar water, we're putting that cell in there, and that is water potential equals negative 5.7339 bars. We want to know which way the water is going to move. It is placed in sugar water with a solute concentration of negative 4.0 bars. How do we do that? Well, we know our water potential for this. Do we know our water potential for the beaker? Not really. We only were given the solute concentration. So how do we figure that out? Well, we plug it in here. And it's telling us again, it's in an open container, so there's no pressure potential there. If there was, it would be given to you. So we know that this is just going to equal negative 4.0 bars. And we also know that water moves from high water potential to low water potential. So which way is our water going to move? High, this one's higher, to lower is here. It's going to move into the cell. All right, practice these, please.